Welcome to a code report solution video. In this video, we're going to be comparing three programming languages, Python, Rust, and BQN, my favorite, against one problem. But this video is about highlighting why Rust is so beautiful. Even though it's not my favorite language, doesn't compare to BQN, but it is extremely beautiful when solving problems like these when compared with Python, which is a fantastic language as well. The problem that we are going to be looking at is find x sum of all k-long subarrays. And the problem states you are given an array of integer nums and two different integers, k and x. You want to look at k elements at a time with a sliding window, and then take the x most frequent elements, and then sum those elements and put that in an array, and do that for each of your k-long subarrays. So hopefully this will make sense when we solve this live in BQN, and then we'll take a look at the equivalent solutions in Python and in Rust. So hopping over to BQN pad, our favorite place to code BQN, we have got a header here which is destructuring our input array into n, k, and x. So n represents our list of numbers, 1, 1, 2, 2, 3, 4, 2, 3. And then k is going to be the length of our subarrays that we're taking, so 6 elements at a time. And x is the number of elements that we're going to be looking for, the top x most frequent, in this case 2. So the first thing we want to do is get our sliding window, which we can do by making use of a function called windows in BQN. So you can see here, because k is equal to 6, we're getting rows of length 6, and into an array of 8 elements, you're going to end up with 3 rows because you're stepping by 1. So the first row is 1, 1, 2, 2, 3, 4, if you look at it like this. Then the second row is just going to be the middle 6 elements, and then the third row is going to be the last 6 elements. And now what we need to do is we are going to build a block, and we're going to perform this block over each of our rows. But for the moment, we actually have to do this over each of our rows after converting it to a nested list, because when we get our x most frequent, we're going to end up with variable length arrays. Therefore, we can't work in a matrix right now. So we need to enclose over each of our rows, and then if we perform this each now, whatever we do, so if we perform a reverse here, it's now going to reverse each of our lists inside our nested list here. So the next thing we are going to do is our classify group idiom, which is going to give us groups of all of the equal value elements, which will enable us to get our frequencies of each value. So for our first list, we had the values 1, 1, 2, 2, 3, 4, and you can see that they're all in sublists now. So in order to get our key value pairs, if you will, of the value and the frequency, we basically just need to do first and pair that with the length, and we're good to go here. And note that we're actually going to want to get the most frequent. So if we switch length with first, we are now going to be able to immediately sort, reverse sort, in order to get our top x. So if we do the reverse sort, we now have 2 that showed up twice, 1 that showed up twice, and 4 that showed up once, and 3 that showed up once. And it also takes care of that second sorting criteria that you always want the largest number. So now from here, we want to do a x take, because x is the number of elements that we want, and that's going to take this. And now we have all the values we want. We have the 2 2s and the 2 1s for our first element or first list. Then we have our 3 2s and our 1 4 and our 3 2s and our 2 3s. So in order to get the sum of all these, we first need to take the product of each of these, and then we need to take the summation of these, which is just going to be a plus reduction. So we've got a plus reduction, a multiplies reduction over each of our lists, and this is almost done. But now that we have a function that we know is going to result in a single integer, we actually don't need to do this each over our enclosed row-wise pattern here. We can just delete these two and apply this over the rows. which is quite nice. So lots of things going on here. We have our reverse key value paired counter or frequency function here. We've got reverse sort, we've got take, we've got a row-wise product or kind of an inner list product, and then we've got our summation at the end here with our windows at the very front. So now let's hop over to Python to see the equivalent of this solution there. So this was our BQN solution, and this is our Python solution. So all of the components or functions that you see on screen are essentially equivalents of what we just saw in Python. We have our sliding window, which comes from the more itertools library. That's the equivalent of our window in BQN. We have our counter, which was the equivalent of the first length pair over the classify group idiom. We then have to invert this with a list comprehension that I've put inside a helper function, because there's no nice way to invert the keys and values of a dictionary. And then once we have this in our nested list form, we can call sorted on this. And from here, we could map our math.prod and then pass that to sum. But that would involve building up lambdas, and the way that the black formatter formats that is very irritating. So instead, I convert this to a NumPy array that gives me the ability to perform row-wise products and a summation afterwards. You do need to call the toList at the end of this. But this is nice as well because you can chain these instead of doing the inside-out thing, which we have to do here with the counter and the sorted methods. Quite nice, if not for the fact that you have to call a bunch of different libraries, language features, collections sometimes in the case of counter. But at least we can solve the moral equivalent of this in Python. Moving over to the Rust solution, which is incredibly beautiful because everything here is inside the iter library or itertools. So we start off by calling our Windows function on nums, which is the equivalent of sliding window in Python and Windows in BQN. And then for each of those windows, we're going to make a call to the function counts, which is the equivalent of our counter collection in Python. Here it's a method on our iter library though. Then we have to call this into iter in order to make it iterable again. The inversion we can do with a simple map and destructuring of the key value pairs and then just reversing them because we have destructuring in the parameter list of a lambda in Rust. We then call sorted, then call reverse, then call take. We have to do a couple conversions here in order to get the right types that we pass to these methods. Then to do our row-wise product, we can just destructure the value and key again, once again, and as conversion needed to I32. Then we just call sum and collect at the end. Now, if you are a Rust developer, you might be thinking that there are a couple different ways to solve this. There's a sort by method, a couple different ways using that so that you can avoid the reverse on sorted. There is a link in the description to a GitHub repo that shows 2 other Rust solutions, but this is meant to be the translation of both the BQN and Python into Rust so that they are comparable. And the reason that I think this is so beautiful is because you don't have to reach for 6 or 7 different things in 4 or 5 different places. If we move back to the table that I showed at the beginning of this video, I showed with color coding basically where you find this stuff. Sliding window is in a third-party library called more itertools. It's not even in itertools. Prod and sum are methods in the NumPy array library. The list comprehension used for inverting the keys and values and the negative slicing are basically language features. Sorted is a built-in method, and counter is a collection found in collections. So you have access to all of this stuff in Python, but it's all over the place, and you need to know where to reach for it and what to reach for. Some cases it's a built-in, some cases it's a method on a NumPy array, some cases it's an itertools, more itertools function, and other times it's a collection in a collection library. Whereas in Rust, everything exists in the exact same place. Link in the description if you want to go check out iterators in Rust and the iter library. It's fantastic. The fact that you have these, everything is in the standard iter library other than counts, which is in the itertools, but they all work seamlessly together. And then you compare this to BQN, where everything here is expressible, if not way more tersely, which is why I love BQN so much. Anyways, links in the description for everything I mentioned. Hope you enjoyed, hope you learned something, and we will see you in the next video.